Good afternoon. My name is Yevgenia Babenko. I am pleased to present our work entitled Cognitive Interaction Layers for Neuro-Symbolic Artificial Intelligence. This study introduces a proof-of-concept framework designed to support cognitively aligned human-AI interaction. Despite the significant advances of large language models in syntactic and contextual processing, they remain limited in semantic interpretation, associative reasoning, and memory-oriented tasks. Addressing these limitations requires approaches that can approximate human cognitive mechanisms. The objective of this work is to develop interaction layers that make computational systems more compatible with human cognition. We propose the notion of cognitive interaction layers. These layers function as human-centered interfaces that embed semantic cues, associative structures, and visual metaphors. Their purpose is to transform static representations into cognitively enriched environments that enhance interpretability, memorability, and knowledge transfer. The proposed architecture consists of three interconnected components. A semantic representation layer that formalizes domain knowledge. A cognitive interaction layer that maps structured knowledge to cognitively motivated encodings. A neuro-symbolic reasoning component that integrates symbolic knowledge with adaptive inference. This layered design provides a foundation for scalable and interpretable cognitive AI agents. The framework was instantiated using RDF and OWL ontologies for structured knowledge representation. Cognitive encodings were operationalized as semantic cues and associative prompts. Simulation of interaction was implemented in Python, with a Flask backend and a web interface. This methodological setup enables systematic exploration of cognitive encoding strategies within knowledge-based systems. Two proof-of-concept simulations were conducted. First, a semantic similarity task applied the proposed cognitive distance function to benchmark datasets WordSim 353 and SimLex 999. Second, a recall-oriented task simulated learning performance under two conditions: a baseline interface and a prototype cognitive interaction layer enriched with semantic cues and visual metaphors. These evaluations suggest that cognitive interaction layers can improve alignment with human similarity judgments and may reduce estimated cognitive load. This table summarizes the simulation outcomes. On semantic similarity benchmarks, Spearman correlation with human ratings increased when cognitive encodings were applied. In the recall-oriented scenario, accuracy improved while cognitive load estimated with NASA TLX-inspired parameters decreased. These results demonstrate the feasibility of the approach, while remaining preliminary and simulation-based. The current implementation is primarily symbolic. Nevertheless, its modular architecture enables integration of neuro-symbolic reasoning components in subsequent iterations. Future research will focus on extending knowledge resources, refining cognitive encoding strategies, and conducting empirical user studies. Promising application domains include professional education, cognitive training, and explainable AI. In conclusion, cognitive interaction layers represent a step toward human-centered AI by embedding cognitively motivated mechanisms into interaction design. The presented simulations illustrate their potential to improve semantic alignment and reduce cognitive effort. We acknowledge the preliminary status of this work and emphasize its role as a foundation for future empirical validation. Prototype code are openly available. They are published on Zenodo, which also provides access to the GitHub repository. This concludes my presentation. Please feel free to send your questions to my email, sarahan@nas.gov.ua. Thank you for your attention.